One advantage of discriminant analysis is that it can naturally incorporate unlabeled data. Sometimes people call discriminant analysis as a generative model for classification because we learn the whole distribution. And next we're going to see how this framework can lead to a natural way to incorporate unlabeled data for classification problems. When I was talking about LDA, I have to keep reminding students that LDA, the algorithm looks so much like the EM algorithm for mixture model, but they are different in the sense that in LDA, Y is given, the label, but in mixture model, in the EM algorithm, where Y is actually unknown, is our latent variable, indicate which component you are from. So in that sense, LDA is actually easier than fitting a mixture model. But the underlying model assumption stay the same for the two models. We always assume given Y, X follows a relatively simple distribution like normal, and marginally Y follows a multinomial distribution. So in this will make LDA a natural model in a supervised learning setting. What is this? In a semi-supervised learning setting. What is a semi-supervised learning? In semi-supervised learning, we have both labeled data and unlabeled data. For example, when you are doing a sentiment analysis, which basically a binary classification problem on movie reviews, you could hire somebody to label the reviews positive or negative. But meanwhile, you can also go online and grab a lot of unlabeled data. So here I colored the unlabeled data as gray, and we don't know the label. In unsupervised learning, we do want to incorporate the unlabeled data into our classification model. Hopefully can help enhance the predictive power of our classifier. Unlabeled in LDA or even QDA and naive Bayes, the unlabeled data can be naturally incorporated because all we learn is the joint distribution of X and Y. And for labeled data, we observe both X and Y. But for unlabeled data, we only observe X. We do not observe Y. So Y is the latent variable. And then we can just use our EM algorithm in our iteration step. We just assign a probability, estimate for each of the Y for the unlabeled data. So the whole framework, which based on EM, can be implemented very easily. So we can incorporate the information from the unlabeled data. Next, I want to share with you a student's project from my last year's Bayesian machine learning course. I want to show you that LDA actually is very useful even for some seemingly very complicated tasks like image classification. So the underlying framework is what I call LDA+LDA, and there are two LDAs. The blue one is the latent dirichlet allocation model, and the second one is the linear discriminant analysis. When we talk about latent dirichlet allocation model before, it was proposed as a way to model or represent articles or text data, where we view all the words in an article as just there's no order information. So we represent every article by just a word frequency. And meanwhile, we have a bunch of topics. Every topic is a multinomial distribution over all the words. And then we're going to model each article as a mixture of those topics. And then every article can be summarized as the mixing weights over those topics. And that mixing weights can be viewed as a new feature extraction for every article, and it can be used for other downstream analysis on those articles. And the same idea can be used to model images, known as a visual words representation or bag of patches. So for example, in this case, we have 3 images, and we're going to chop them into small patches. And then for every patch, we can not way like it's well known in the computer vision. There's a way we can extract some feature measurements on every patch, and like the sift feature. So every small patch now is a data point in a, let's say, p-dimensional space. So we have a lot of patches, a lot of data points for every image, and then we can grab all the patches over all the images. Those are data points in some, let's say, p-dimensional space. And then we're going to just simply run a k-means algorithm to divide those data points into different clusters. In this case, our k is equal to 4. So we're going to run a k-means with k equal to 4. And then we're going to go back to look at every image. For example, let's look at the first image, and we're just going to count how many patches from image 1 is from cluster 1, how many from cluster 2, 3, or 4. So that percentage is represented by that histogram. So that's the mixing weight for image 1, and we can do the same for image 2 and image 3. So that 4-dimensional mixing weight now is a new feature representation for every image. And then we can use that 4-dimensional feature as an input, as our x, in our linear discriminant analysis, and to build a classification model to classify those images. So that's a framework, LDA plus LDA. So last year in my course, a student took a project. It is an image classification, and her images are splatter patterns of some liquid, look like this, and you can sort of see how the water pattern are different in the 3 images. So her image is very much like this. I don't want to explain why she wanted to work on that. It's actually related with some company at the research park. Nowadays, if you want to do image classification, the basic hammer is deep learning. So she tried deep learning, and indeed worked out very well, and that boost the performance from the initial 50% to 95%. That's a multi-class classification problem. And then she tried a lot of different implementation procedure for deep learning, like dropout and certain tuning, and eventually she can boost the performance to even higher than 95%. And when she was preparing the final presentation and the final report, we had a meeting, and I looked at her image, and it just occurred to me, maybe because the pattern is like, clearly you see some of each image has the splatter patterns are different, and some is a mixture. Like there's a natural way of thinking about every image is a mixture over some basic patterns. So I asked her to try this LDA plus LDA approach, and a week later she came back, said, well, the performance now is 100%, the test error. So which is wonderful. And also her boss is pretty happy because that latent Dirichlet allocation representation helped them to understand how those classes are different in terms of the splatter pattern. So my point is LDA, although it is a sort of a simple algorithm, but if you can find a good representation of your of the objects, it can be a very powerful method. The main issue with LDA, and I usually would worry, is high dimension, because the algorithm itself sort of estimate all the parameters in some standard way, mean, covariance, and put them together, and there's no natural way to add a variable selection there. So if you have a high dimensional problem, I would always suggest you to do some pre-screening to reduce the features to a smaller set of features. This is especially true for naive Bayes. One of the screening procedure I mentioned before is just the marginal screening. In this case, will be a 2-sample t-test. So what is a 2-sample t-test? And here's our data. If you look at the features, there are p features. we're going to try a 2-sample t-test for every feature. So let's first look at the first feature. So I put a black box around all the data, and they are from first feature. So there are n of them, and some of them are from the blue class, and some of them are from the red class. So you have two groups. You have data points, one-dimensional, from two groups, and you want to know whether the means are different, indeed are different in the two groups. So that's called a 2-sample t-test. You can call an R command called t.test, and you can get a p-value from this, and you can do this for every dimension, and then so you get a p-values, and you can rank them, and you can drop features with large p-values. Because when p-value is large, it means that when we look at the data points from the blue and the red for that particular dimension, we don't see significant difference among the two groups. And this procedure, of course, is not ideal in the sense we could miss some good features, because when we are doing this 2-sample t-test, we treat each feature separately. We won't allow them to cooperate. So it is possible we could have a pair of features marginally that look similar, for the blue and red group, but when they work together, they're actually very powerful. And that's true. So that's a sacrifice, that's a compromise we have to make when P is large. When we apply those screening procedures, it is possible we're going to drop some gems, but hopefully the whatever left there are still very useful. The second approach is called regularized discriminant analysis. Again, is just try to avoid the overfitting problem. I used to cover this in my course, but now I just feel it's no longer that relevant. I'll explain why, but let's just take a look of this RDA. The RDA want to continue with the QDA, quadratic discriminant analysis framework, where we going to model data from every class as a normal with a different mean and a different covariance matrix sigma k. But instead of estimating sigma k, like the class-specific covariance, only using data from the case class, where now the new sigma, which is group-specific or class-specific sigma, is actually a weighted average of 3 elements. What are the 3? First, we're going to estimate something called sigma k, but with a parameter lambda. So it is a weighted average of the group-specific covariance and the pooled estimate, which is estimate based on all the data from all the groups. So it's a weighted average of these two, meaning we're going to going to shrink our group-specific covariance matrix toward the sigma, which is a common covariance matrix shared by all of the classes. And that's the first step, weighted average. But then we're going to do a weighted average of the sigma k lambda using another weight gamma with a diagonal matrix. Okay, so our final sigma hat is an average of the original of the covariance matrix from original QDA and the covariance matrix from the original LDA and some kind of identity matrix. And here are tuning parameters. You can see how this framework can be used as an umbrella to contain all the previously mentioned procedures. You can check the value, for example, when gamma equal to 0, lambda equal to 0, the smallest regularization, so you allow the maximum difference, meaning every group K can have their own covariance matrix. So that's back to the QDA. And with another type of verbal selection, you get other type of choice for lambda and gamma, you get LDA. You won't get exactly the naive Bayes, because in naive Bayes, our covariance matrix is not identity but diagonal, so it's slightly different. And the last one is the simplest one, where gamma equal to 1, lambda equal to 1, and you can find out our sigma k hat is basically a diagonal matrix, but the diagonal entries are all the same for different dimension and for different classes. So you're going to find that in that case, if we further assume the mixin weights are the same for different groups, then the discriminant function or decision function is essentially just the L2 distance of a point to those case centers. Meaning you get your training data, you calculate the centers for the capital K classes, and when a new test point comes in, just compare its distance to those case centers and assign it to the closest center. There is a package in R so here's a lambda and gamma can be tuned through cross-validation, and you can, if you want to know more about this, you can check the R package for RDA or find out the original paper by Freeman on RDA. The reason I feel that it's no longer very useful because nowadays when we estimate those covariance matrices, another type of regularization we like to use is just to require it to be sparse, meaning only a small number of elements will be non-zero. So it's different type of regularization, and like people use a different type of regularization nowadays. Okay, so I think I'm done with the regularization and those additional discussions. At the end, I wanted to address the issue about categorical variables in R, because I noticed some students are talking about this on the forum. A key question people want to know is, if we have a categorical variable, should we treat it as a ordered factor or an unordered one? My answer is it does not make any difference for linear regression model. So here are the examples. We're going to generate a fake data y, and our fake feature x is a categorical variable with 3 levels A, B, C. So we have 6 observations. The first 2 is from category A. The middle 3 are from category B, and the last one is from category C. So when we fit a linear regression model and treat x as a factor, unordered one, by default, R will assign the so-called treatment contrast, meaning R recognize A, B, C are the category labels, and by default, they are ordered by their alphabetical order, and A is ranked the first one, so it's treated as a reference group. So this is why if we look at our design matrix, we only need to generate 2 columns in addition to the intercept, and the 2 columns are basically the one hot coding for category B and category C. And we can also fit a linear regression model where I add -1. So this is telling R that don't include the intercept. And then R will basically generate this what I call a naive coding for categorical variable. They are basically one hot coding for the 3 categories. And this is a nice design matrix because all the columns are orthogonal to each other, and you can easily find out, well, if we use a design matrix like this, my coefficient 1, the first one will be just the average of the 8th group or 8th category, and my coefficient 2 will be the average of the 3 observations from category B, and my last one is the average, which basically just the observation for the category C because it has only 1 sample. So I want you to know that for categorical variables, it's enough just to remember them using this naive coding, which is this. It's good to think about your design matrix like this because there's no difference. The other, for example, this design matrix, this one, is basically a linear transformation of this naive coding. Next, let's look at other coding schemes in R for categorical variables. Again, there's no order. So here I'm telling R to treat to set the contrast for my categorical variable x as the sum contrast. And this is basically telling R what is the code book for this categorical variable, because it has 3 levels, so we need to generate 2 columns. So the code book is, the first column is telling R how to generate the first column. So if observations from category 1, you're going to code it as 1. If you're from category 2, you code it as 0. If you're from category 3, you code it as -1. So that's how R code this column. And this column is telling R, this is a code book for coding the additional, the second column associated with this factor x. So if you're from class 1, you're coded as 0. From class 2, you code it as 1. If you're from class 3, you code it as -1. Now you can look at this design matrix and then go back to look at this naive design matrix. You're going to find out this matrix is basically a linear transformation of this naive design matrix. So my point is, you could try different contrast. You can get different design matrix, but they just a linear transformation of each other. So the coefficients might be different, but your y hat, your r square, sigma square should all be the same, because the underlying space spanned by the column of the x should be the same. Next, let's try another type of a coding, and it's called a poly. So again, this is telling R, this is a code book for R to generate this column and this column. Now you can pause the video and see whether you can use this code book, whether you can generate this x.l or x.q. So this is called this is called the poly contrast. So far we treat our x as an unordered factor. Next, I'm going to just tell R, well, we want to order, and I want to generate a factor which is similar to the original x, but now I want to treat it as an ordered factor. So for ordered factor and factor variable, by default, R is doing this poly contrast. So this is why the design matrix is the same as what I shown you here. So I copy that one on the right. Okay, so at the end, we actually have talked about 5 different regression models for the same data, depending on how you, for example, the first one is using naive treatment contrast, just regular treatment contrast, and the second case is what I call the naive contrast, where we basically fit a model without the intercept, or not without the intercept. We tell R, we're not going to have an intercept in the model, so R will generate 3 columns. And we also try the model with the sum contrast and poly contrast, and the last one is going to be the regression model, where we treat our categorical variable as an ordered factor. So I show you 4 columns, and the first column is sigma, which is the standard error from the 5 models, and they are all the same, because as I mentioned before, when you change the contrast, and your design matrix will be different, but the underlying space is the same. So your y hat, residual sum of square, everything, and about the fitting of your model, and it's the same. But it is true the coefficients are different. So the last 3 columns are the coefficients. They are different. So the final conclusion is that for factors, it doesn't matter you want to treat it as ordered or unordered, and it doesn't matter what kind of a contrast or code book you want to use to code them. There's no difference if you look at the y hat, the fitted value or prediction. But it is true the variable selection result will be different, because your coefficients are different, and it is possible with one type of coding and you can get sparse coefficients. But for any real data analysis, you really don't know what kind of a coding will be optimal, and I would feel it's fine to use just the basic one-hot coding, so you don't need to try different coding schemes, and you can just treat them as an unordered factor, and let the regression model, through variable selection, or use a tree model, and to figure out what levels are more relevant.